Thank you very much for inviting me to give this lecture on the different cardiac source models for the inverse problem of ECG. The contents are quite a lot for 15 minutes. I like to point out that I started 4:30, right? Source models, what do I really mean with it? I will look into EP and endocardial potentials, impressed currents, transmembrane voltages, equivalent double layers, the divergence of the gradient, another single layer source, and then I will try to compare all these sources. So I have to go back to the basics of bioelectric signals. And what we learn is that we have cells in intracellular and extracellular domain, and in the depolarization front, where the transmembrane voltage moves from, let's say, -80 to +20, we have on one side currents that go from the inside to the outside of the cell, and on the other side, currents that go from the outside to the inside. These are capacitive currents. These are the sodium inward currents. These will be in the following called the impressed currents. And the impressed currents behave like current dipoles. A current dipole is in principle a little piece of line where a current is flowing, current I is flowing, and if the length is D, then the current dipole is current multiplied by D. And with this, I have to torture you with some equations. I cannot hide that I give a lecture on electromagnetics and numerical calculation of fields. But I would say I try only to give the idea of these equations, and then you can have the slides. If you send me an email, I will immediately send you the PDF so that you can go through all this in detail and find out whether the mathematics are really true. So here is the idea of the impressed current density, which is conductivity times the gradient of the extracellular potential plus some impressed currents. This is the total current density, and this is the impressed current density. The idea of the impressed current density is not really new because if you go to field theory and find the equations that combine the electric field and the polarization vector and the magnetic field and the magnetization, you find absolutely similar equations like that. And these equations up here, they come from, they are aiming at a homogenization in the material that is known from theoretical physics already for a long time. I have learned this from a textbook of Landau and Lifshitz of theoretical physics. And so you can go from microscopic electric dipoles to the polarization, and from microscopic magnetic dipoles to the magnetization. It's a homogenization process. And precisely the same happens here. You just copy these equations and translate them to this type of equation. I'm so much discussing this here because this was an equation that Günther Scharf in some way accused. And even though I'm very sad that he passed away, I have to say these equations are very powerful, and they do not come from somewhere from heaven, but they come from a very thorough homogenization process, basically the same that you find here. Then from here to here, it's just a translation from the real conductivity tensor to a bidomain conductivity tensor. And then from these equations here, in a few lines, you end up with this equation here for the general case of unequal anisotropy ratios. If I say you come from here to here in a few equations, I hate this formulation because sometimes you can struggle for hours with this, and because of that, here are the equations. You can find them in the handout, but obviously this is not the place and the time to discuss it, but you will see it is really only 10 lines of mathematics, and from here you end up here. Then this is a kind of Poisson equation, but not really. And there are two steps with which you can move this to a real classical Poisson equation. Here I introduce equal anisotropy ratios, then this formula is true. And here I even introduce isotropic conductivities, then this which is originally a tensor boils down to a scalar. You can divide by it and you end up here. And again, I say there are only a few lines of mathematics to go from here to here. And these few lines of mathematics are outlined here on the following page. So I will not discuss these equations, but I tell you it is in the handout and it is really only a few equations. We need to have also obviously some boundary conditions. So I skip this nice mathematics, and I now say we should all believe that this equation is true. And what we see here is on the one side, the sources, the source term, and on the other side, the potentials, the extracellular potentials that come up from it. So if we go here, we see the transmembrane voltage. This could be a kind of source of our problem, but hidden behind the gradient and the divergence operator. Then we could multiply the gradient of the transmembrane voltages with the conductivity tensor, and we end up with a unit that with a property that is amps per square meter, and that is an impressed current density. This is a vector. The gradient multiplied with the tensor is a vector field. And here is the divergence operator. It makes out of all this, again, a scalar property. So the divergence of the impressed current density, all this could be a source, and I will discuss that. We can do as if the transmembrane voltage is the source, as if the impressed current density is the source, or if the divergence is a source, whatever you like or what you would think is best. On the other side, we have what follows from these sources, and this is the extracellular potentials. So I always hesitate in saying if you reconstruct the extracellular potentials, it is not precisely, in the mathematical sense, you do not precisely reconstruct the sources. You do a deblurring. A deblurring so that you try to find the field inside a body from the field outside the body. And so that's, I think, all that I explained already. And so I can say here, I'm a little bit proud that Oleg Skipa from my group introduced the idea to introduce the transmembrane potential reconstruction into the community in 2002. And here I would give some extra hint. Since the transmembrane voltage is hidden behind the differential operator here, you can add an arbitrary offset and end up with the same potentials. And you can also say this on the other side, because also the external potential is hidden behind the differential operator, and that means like all electric potentials, they are only defined with respect to a constant term that you can add anytime you want. Now, this is again only for the experts. You can go through these equations if you like, but the message at the end is if you start with the equation that I just showed, you can bring them into a different form. And this form here is precisely the same form that you have if you add, let's say, hundreds of electric dipoles and find the electric potential. Only that here we have our current dipoles here, conductivity gradient Vm. These are the current dipoles, and you can reconstruct in a large homogeneous conductor every potential via a superposition of hundreds of little electric dipoles. So this is kind of proven mathematically here, and here you see the equations where it comes from. Also this here I will not explain, but I will tell you that I think it was the first was Geselowitz, but also then Adrian van Oosterroom spent a lot of time on this. Via these few equations, you can translate this into this equation, and here you see we only look into a surface integral. This is a surface around the heart, and so we project all our sources into the surface. And this is possible if we have a scalar conductivity tensor, and it might also be possible if you have equal anisotropy ratios. then you can replace all the sources by the sources on the surface, and that is the transmembrane voltage on the surface. And this is the auto-solid angle from the electrode to this area on the heart, and you just multiply here, and then you get the electric potential. This is a beautiful step that has been used for the equivalent dipole layer. The equivalent dipole layer is defined in the papers of Peter van Dam and Tom Ostendorp in this way, but you basically see it's this factor here, and it's this difference of the transmembrane voltage in the depolarized in the resting area. And so you translate all the sources to the surface and only look at the outer solid angle to the surface where you see the depolarized area. Now, I can also go one step further. We have seen the transmembrane voltage. We have seen the gradient of the transmembrane voltage or the impressed currents. And now I take the divergence of all this, and I go to the case of scalar conductivities. And I see here is the Laplace, and here is the source term. And if you compare this with what you have learned in electrostatics, then you have the Laplace equation or the Poisson equation, where on this side are the sources, and these are in this situation the charge densities. So mathematically, it is equivalent whether you talk about the divergence of this with the transmembrane voltage or whether you talk about charge densities. So here in this area of the depolarization front, you have a layer of positive divergence, and here you have a layer of negative divergence. I would prefer to interpret this in the sense of impressed currents, but from the mathematical point of view, it's absolutely equal to do as if this is a positive charge density and this is a negative charge density. And with this, I think this is precisely what Günther Schaaf said that, and what is now used by acutors. So this similarity tells us this is really obviously a nice source model. It is not really new, I would say, but it's the divergence of this here, but it's an interesting approach. And then here with this, I refer to the paper last year published by the EP Solutions group by the Kalinin brothers. And they say they do as if we have also the Laplace equation inside the heart, which is wrong. But with this trick, you also project all the sources on the surface. And with this trick, they also can get nice results. So it is a new and slightly different type of projection of all the sources onto the surface of the heart. And here I would like to, well, maybe makes it a bit more visible what I mean with sources and with the fields. Here in the front of the depolarization layer that moves to a piece of myocardium, here are the sources. And in color code, you see the electric field. So the electric potential already starts quite a long time before the front reaches the electrode. And it's still going on for quite a long time when the depolarization front is already far away. And only in the moment when the potential goes, the amplitude goes to zero, that's the point where you really have the sources beneath the electrode. So in the kind of discussion, I would say, how do epi and endocardial potentials, is it a good source? On this side, I have the transmembrane voltage. On this side, I have the epi and endocardial potentials. And of course, you can see the wavefront also in the epi and endocardial potentials. But you can also see far fields. Ventricular far fields will also lead to signals on the other side, and that's not where the sources are. My comment would be the surface on the myocardium are now near to the sources, so that the zero line between red and dark blue is where the wavefront is. This is nice, and it can be validated with catheter measurements, but keep in mind the transfer matrix to the endocardial side is nearing zero. Far fields will also lead to non-zero epi and endocardial potentials, even if the sources are far away. It's the borderline between red and blue that shows us where something interesting is going on. Pericardial potentials are also interesting, but I see I do not have the time to discuss that. And I think I also have to skip this nice picture that Steffen gave me last week. So this is now the impressed currents. The impressed currents are here at the front. Here at the front, we have impressed currents, and we can see them from far away. Then there would be just one single large dipole. We could replace this by a single large dipole that is normal to the surface. And this has been used by the group of Ben Hay for a couple of years with nice results. But with this impressed currents, if there is a depolarization front here, we only have an impressed current in the plane. And so we cannot always do as if the impressed current is orthogonal to the surface. So what is good and bad with the impressed currents? The number of unknowns is 3 times the number of knowns because the impressed current density is a vector field. And the spatial resolution is too bad to show all the details of the impressed currents. Cannot really be approximated by a normal, by an in-plane vector, and global averages might be misleading. So you see, my comment is I'm not very happy with this. Are the transmembrane voltages a good choice? Yes, I would say yes. There is a standard time course from re to depolarization. We show what's really going on the tissue. We would, and in principle, do not see far field. But the problem is even more, this is fine, but as soon as the whole heart is depolarized, we get to 0, or we use some tricks. And keep in mind, the depolarization fronts are nearly invisible before breakthrough, because the transfer matrix is very bad. This is then the double layer. We go to the surface, we project all the sources on the surface, and this is very effective because we boil down the number of nodes significantly compared to transmural images. Still, we have a standard time course from read to depolarization, and we still show the real activity and not the reaction to faraway sources. So this is something that I really would say is a very good choice. And now we come to the charge density. We can translate this front into a layer of positive and a layer of negative charges. And I think this is also a very nice source model, because again, we boil down the number of nodes significantly. We only look to the surface. We try to look to the local activity of the tissue itself and not to the reaction by faraway sources. But we have to neglect the unequal anisotropy ratio, and the region of positive and the region of negative divergence are very near. What is left after blurring due to the ill-postedness? And finally, this picture is quite similar to the epi and endocardial voltages, but it has some advantages. It seems to be a bit more sharp. And at the end of this talk, I come to the end of this talk, luckily, I want to refer to work that Steffen has done. He says we have to look into artifacts. What is really a good source? You see here transmembrane voltage, epi and endocardial voltage, pericardial voltages, and then different types of reconstruction techniques. And we would now, after we have gone through all this, say we should look at those reconstruction techniques that have the smallest amount of artifacts. And many of these produce artifacts in the LAT map, the local activation time map. And they have been reported by Duchateau also in real cases. So they are really a problem. And we think that transmembrane voltages are not so prone to this problem. And this is then Steffen's lecture. So with this, I like to say thank you. And of course, I'm open for the discussion.